me a second. So, let's go out back. So, you know, we've got these 6 chickens. And they lay eggs for us every day, but it's been a long time since we've collected the chicken eggs yet. Hello, girls. Morning. So let's see how many we have. Excuse me. Hello, ladies. Uh-oh. Hello, young lady. Oh no. Look what we have. 2, 4, 6, 8, 10, 12.
Oh my gosh, I just thought of a really cool real life problem using proportional relationships.
Oh no.
So, if our chickens lay 3 eggs every day, and you've got 12 eggs there, how many days has it been since we've collected eggs? Okay, see you inside. So if you said that it had been 4 days since we've collected the eggs from the chickens, you were correct. Proportional relationships, that was the topic of the last video in this series. The next one will be on analyzing and solving percent problems. My name is Laura Chang, and I am a teacher with Seattle Public Schools, currently teaching math at McClure Middle School. Thanks for joining us. Whether you're a student, a parent, a teacher, or someone flipping through the channels just wondering what's good on TV, I'm glad you're here. Go ahead and grab a piece of paper and a pencil or something to write with and join us during this session. Try to answer the questions that are on the screen, take some notes, really own this learning. Today, we are going to be focusing on 7th grade math, analyzing and solving percent problems. We're going to look at a real-life problem from a real-life student. We'll do a concept review, including some vocabulary. We'll model and solve the real-life problem by connecting percent and proportion, by using the percent equation, and by looking at percent error. Then finally, we'll wrap up today's lesson with a which one doesn't belong. So sit back, relax, and let's do some real life math. Oh, here we've got our first caller.
Hi, my name is Danny, and I'm an 8th grader at Holy Trinity, and this is my real life problem. So we've been out of school for about a month now, and one of my favorite things to do is bake. So I went to the store and got all my ingredients for cupcakes. Then I went to pick out the icing, only there are a bunch of different colors in different size containers. The pink icing container had 3/4 cup of icing, the green icing container had 1/2 cup of icing, and the blue icing container had 1 cup of icing. I plan on making 30 cupcakes. It's for my sister's party, and you know, she's not having 30 guests, but I'm sure my dad will eat them all. So the problem is, if I want to use all of my icing, what percent of my cupcakes will have each color? Can you give me some ideas?
So what do cupcakes have to do with percents? Turns out there's a lot of ways to look at percentages. I like the problem that Danny posed. So let's break it down. Okay, so Danny wants to bake 30 cupcakes for her sister's birthday party, then frost them in 3 colors, pink, green, and blue. Oh no, the icing is sold in different sizes of containers. She says she wants to use up all of the icing that she buys, but how many of each color of cupcake will there be? How can she use percentages to figure this out? Before we begin, let's have a little fun with estimation. Estimate how much icing is in the rectangular container using cups or fractions of cups. What do you think would be too small of an estimate? What do you think would be too large of an estimate? Try to come up with an answer before I show you the next slide. If you guessed about 2/3 of a cup, then you were correct. Sometimes estimation can be really useful when dealing with percentages. Okay, time for some concept review. We're going to try to match the words at the top of your screen to the pictures or descriptions of the terms at the lower part of your screen. See if you can figure it out. I'll give you about 10 seconds before I show you the answers. So did you answer percent equation for number 1? If so, you are correct. Part divided by whole equals percent, or part equals percent times the whole. Both are representations of a percent equation. For number 2, 4% of $3,650 in sales represents commission, which is incentive pay for salespeople to sell more. So there's the word of, 4% of $3,650. If you look at the percent equation, we can sometimes think of meaning multiplication. So 4% times $3,650 is what a salesperson would be able to take home as extra pay at the end of a month or a year or whenever. And number 3, 4 over 5 equals 80 over 100 represents equivalent ratios. Remember, you can multiply a ratio by 1 or by any value over the same value, or you can divide it by a value over the same value to get an equivalent ratio. So, for example, 4 over 5 times 20 over 20, which is the same as saying 4 over 5 times 1, would give you 80 over 100. You could also say that 80 over 100 divided by 20 over 20, which is the same as saying divided by 1, would give you 4 over 5. For number 4, 3 of 11, 11 represents the whole. So remember, in the percent equation, part times whole equals percent. So 3 of 11 is that piece of the percent equation. Then in number 5, 0.03 or 3/100 represents a decimal. If you multiply that decimal by 100, you would get percent, or 3%. And then 24 of 90, again, if you think of the percent equation, 24 represents the part. Part times the whole equals percent. Here we have basically the definition of percent error for the first one. A percent error describes the accuracy of an estimated value as compared to an actual value. We'll take a look at percent error later on in this video. The next one, the percent change, describes how much a quantity has changed when compared to its original amount. So we think of examples such as markdowns. Percent change could be markups, like a sales tax. And again, we will visit this at the end of the video. And when solving percent problems, set up a proportion. For example, part over whole equals P over 100, and that would be your percent. Okay, so back to our problem. If Danny wants to use up all of the icing, what percent of the 30 cupcakes will each color be? So we're going to break this problem down into a couple of parts. You might want to take some notes. You might want to write some of this information down. So Danny estimates that she will be using the icing for 30 cupcakes, as that's what the recipe calls for. And she has to use up all of the 3/4 cup of pink icing, the 1/2 cup of green icing, and the 1 cup of blue icing. So how can we analyze and solve Danny's problem using percents? Before we begin with the actual problem of how many of the 30 cupcakes will be green, pink, or blue, we can look at what percent of the cupcakes each color will be by looking at what fraction of the total number of cupcakes each color will be. So let's look at it like a fraction, part over whole. So for the green cupcakes, we want 1/2 cup green icing. For the pink ones, 3/4 of a cup, and for the blue ones, 1 cup. So how much total icing do we have? Well, in order to figure out the total, we simply add all of those parts together. So 1/4 plus 3/4, I can have a common denominator in order to add the 1/2 and 3/4 to get 5/4. 2/4 plus 3/4 is 5/4, and if I turn that into a mixed number, that would be 1 1/4, and if I add that back to the 1 cup of blue icing, I have 2 1/4 cup total icing. So let's start out by connecting percent and proportion here. I want to know what percent of the total amount of icing is each color. So I could start out first of all by representing the 1/2 cup of green over the 2 1/4 total. And that's a complex fraction, but that's still equal to x over 100. But to solve that, I think I want to convert the fraction to a decimal and say, well, I'm going to go ahead and write 0.5 over 2.25. And that's going to equal x over 100. That's just going to make the math a little bit easier for me to solve if I'm using a calculator. Then I'm going to do the pink, which is 3/4 of a cup. As a decimal is 0.75. And we said the total amount of icing that we have when we add those three up again is 2 1/4 cups, which is 2.25. And then finally for the blue icing, we've got 1 cup. I can write that as a decimal, 1.00 over the total, 2.25. And again, that's equal to x over 100. Okay, all that's left to do now is cross multiply and solve for x. So for the green frosting, we know that 0.5 times 100 is equal to 2.25 times x. So moving the decimal place over twice, because when you multiply by 100, you are moving the decimal place over 2 times to the right. So 50 is equal to 2.25 times x. Divide both sides by 2.25 to get the percent of frosting that is green. So 22 over 100 is equal to 22%. So x is equal to 22. For the green frosting, for the pink, we have 0.75 times 100. Again, recognize that this is kind of like a pattern because we just did this for the green. Now we're doing it for the pink. We multiply 2.25 times x, again moving the decimal place over 2 times, so we get 75 is equal to 2.25 x. Once again dividing both sides by 2.25 to solve for x. We will get approximately 33. Put this decimal point there. 33 equal to x. Now remember, 33 is what is going over 100, so 33 over x actually represents 33%. And with the blue, we have the same sort of setup, 1.00 times 100 equals 2.25 times x. Once again, solving for x by dividing both sides by 2.25 here. I'm just going to cancel out the 2.25 so you can see what we're doing. 100 divided by 2.25 is going to give me 44. So 44 is equal to x for the blue frosting. So what we see is that this is the percent of frosting that is blue, 44%. And then again for the pink, 33% of the total frosting is pink, and the green, 22% of the total amount of frosting is green. So for the next part of the problem, we are going to model and solve using the percent equation. We want to know how many cupcakes of each color will there be. Well, let's remember our percent equation is part equals the percent times the whole. And we already figured out that 22% of all of the cupcakes will be green, 33%, approximately 33% will be pink, and 44% will be blue. So all we have to do is multiply by changing the percent to a decimal and multiply. So this becomes 0.22 times 30, which is equal to approximately 6.6 or 7 cupcakes. 33%, if I multiply 0.33 times 30, I will get approximately 9.9 or 10 cupcakes if I round it up, and 44% of 30, I would do 0.44 times 30, and that's going to be approximately equal to 13.2, but you can't really have 13.2 cupcakes. You can have 13, so we're going to round it down to 13. And it's great if I add 7 and 10 and 13, I do indeed get 30 cupcakes. So out of 30 cupcakes, 7 of them will be green, 10 of them will be pink, and 13 of them will be blue. So how can we use percent error when dealing with percentage problems? Well, let's just say that Danny estimated that she would make 30 cupcakes, but the recipe actually only made 24. What is the percent error of the recipe? In other words, by how much was the recipe off if it said it would make 30, but it actually made 24? So in order to do this, we need to remember that your percent error is the change or the difference between the estimated and actual amount divided by your actual amount. So you take the absolute value of 30 minus 24, which is the difference between the estimated amount and the actual amount of cupcakes that were made, and divide that by 24, which is the actual amount of cupcakes made. 6 divided by 24 is equal to 0.25, which is 25%. So the recipe was off by about 25% in stating that it would make 30 when it actually only made 24. And that is your percent error. So here's what I'd like you to do. If you have 24 cupcakes instead of 30 cupcakes, how many cupcakes then would be green, pink, and blue? And remember that we have 22% of the icing is green, 33% is pink, and 44% is blue. So now, how many cupcakes would there be of each color? So hopefully you were able to pull out your calculator and do 0.22 times 24 to get 5.28, or approximately 5 cupcakes that were green. 0.33, or 33%, times 24 to get 7.92, or approximately 8 pink cupcakes. And then 0.44, or 44% of 24, so times 24, equal to 10.56, or approximately 11 blue cupcakes. So you add those together and you indeed get 24 cupcakes. And finally, I said I was going to talk a little bit about percent change, so I'll give you a very quick reminder review about how that works. So to find percent of change, which is a ratio that compares the change in quantity to the original amount, you divide the amount of the change by the original, and then you multiply that by 100. So for example, if you wanted to find the markdown, which is a percent decrease, such as a sale, you divide the absolute value of the change in the amount that was marked down by the original amount. So if I had a macaron cookie that was priced at $2.50 and there's a sale on it and I'm selling them for $2.25, I would subtract $2.25 from $2.50 to get 25 cents divided by $2.50, which is the original amount. That would give me 0.1, or 10%. So it'd be a 10% decrease in the amount that I'm selling it. For a markup, which is a percent increase, such as a sales tax, you want to divide the absolute value of the change by the original amount again. So for example, if I decided that the almond flour was too expensive and I had to sell my cookies for $2.60 instead of $2.50, I could say that the difference, the absolute value in the difference of $2.60 and $2.50, which is 10 cents divided by $2.50, would give me 0.04, which is 4%. So if I sold those macarons for $2.60 instead of $2.50, that would represent a 4% markup. And to end our lesson today, I've got a which one doesn't belong. Take a look at the card, think about it for a few moments, and see if you can figure out which one doesn't belong. Wow, I guess that's all the time we have for today. Time really does fly when you're having fun. Thanks for joining me, and tune in next time. And remember, it's always time to do some real life math.